Morning and welcome to everybody. I can see 260 people on this call. My goodness, it's just been getting less and less as the semester goes on. You guys are getting tired, I think, but I'm glad to see 270 of you now here, so welcome. Actually, it's a little early, right? Time is still 11:09. Faison was asking about tips, advice, tricks for multiple choice questions. I think the biggest thing for this class for multiple choice is time management, right? This is a very strange format in that you can't just do the easy questions first. You have to do the questions as they're coming at you, and they're coming at you in this random order. So what you have to do is give yourself this sort of a fixed maximum amount of time for each question and try to judge for yourself if it should be a sort of fast conceptual question and try to do it in a minute or so, or if you need like 3 or 4 minutes to really try to work through something carefully. And so getting your confidence up on how to estimate your time is pretty important. Some questions coming in about the rubric for the midterm. Can talk about that more maybe on Wednesday when we actually get the midterm marked. Final exams, same format. So the exact same format we've been doing for the midterms, that will be the format for the final exam, except it'll be half multiple choice, 10 multiple choices questions in a half an hour, and then half written, where it's 2 written questions in a half an hour as well. Are we ready to share the screen here? Make sure my chat's here. Participants. Okay. Q&A. And don't forget that a week from tomorrow, so 8 days from now, there's going to be another multiple choice test that's called Midterm 5, and it will be based on chapters 9 and 10. We're finishing up chapter 9 today, and Wednesday we start in on chapter 10. And so everything through Monday of next week is testable for this multiple choice midterm on Tuesday, December the 2nd. So the nice thing about a gyroscope, once something is spinning, is that it tends to want to keep its rotational momentum, not inertia. Rotational inertia is that I, it's like the mass, but rotational momentum is a vector which shows which way something's spinning, and it's a 3-dimensional vector, right? So once if there's a little spinning object inside your phone, which there is, and if you try to tilt it, it resists that motion, and it's hooked up to all these little piezoelectrics, which as you tilt it, it senses the resistance to that motion, and your phone can know if it's being turned in 3-dimensional space. So we're not going to get to chapter 6, 9.6, section 9.6 on tides and Earth's day. I mean, it was good to read it, but I'm not going to test you on that, so I'll make that update. So let's start with a quick poll question, which is about, again, rotational momentum. So the question is, a person spins a tennis ball on a string in a horizontal circle so that the axis of rotation is vertical. At the point indicated below, the ball is given a sharp blow forward in the forward direction. So how does that change the rotational momentum L? Does it change it in the X direction, the Y direction, or the Z direction? You can see the sort of 3-dimensional axes there. The trick here is to try to remember the right-hand rule. Sort of a waking up kind of poll here. Good morning. Let me just give you 5 seconds to click in. Okay, let's see what people are saying here. Well, it's just all over the place, 38% to 24% to 40%. So, so what I think is going on is that this thing is spinning in this direction. It's almost like it's maybe a particle on an object which is rotating in that direction. So what you do is you take your right hand, thumb goes up, and your fingers, I'm not very good at drawing, but kind of go around like that. So there's your knuckle. There's your thumb. So I think it's plus Z. So that 40% of you got pretty good. Pretty good. Pretty good. Okay, that's that. And this is this idea that Akina has of this conservation law. So actually, to kind of recap, when we talked about momentum, we said that when the external impulse, okay, so as force over time, when the external impulse in a system is 0, then the momentum, lowercase p, of that system is conserved. So final equals initial. Then when we got on to energy, we said that when the external work done on a system is 0, then the energy of the system is conserved. So it's final equals initial energy. Well, now we're saying if the external torque on a system is 0, then this rotational momentum, which I've been calling angular momentum, but it's in the textbook, it's called rotational momentum. So rotational momentum and angular momentum are two different words for the same thing. It's this capital letter L. When the external torque is 0, then L is conserved. And so what I want to do is do a couple of demonstrations. So one of the main reasons that I was thinking of working from home, but one of the main reasons I got on my bike and rode through the snow to get here today is because Pius has a really good demo set up about angular momentum. So just quick little poll here. If I have two masses in my hands, let me just relaunch this. 2 5-kilogram masses. If my arms are outstretched, A, or if my arms are held in towards my chest, which has a greater rotational inertia, I? I can grab the masses. We're about to do this demo. These are the 5-kilogram masses. So there's me. I'm sitting on a chair, which has greater rotational inertia. I guess C should be that they're the same. You guys. Yeah, so it's A. When you distribute more mass away from the rotation axis, then the rotational inertia goes up. Remember, we did that with this. It tends to want to spin more. It's got more rotational inertia. So good. The first demonstration I'm going to do, involve that, is there's going to be 0 external torque because we've got a good frictionless chair there. I'm going to begin rotating at some particular value of omega. This is this rotational speed. Do you remember the units for that? It's radians per second, is the units. And with my arms outstretched, and then I'm going to bring the masses into my chest. And so the question is, what's going to happen? How does it affect the rotation speed? You have to try to judge that. Demonstration 2, if I'm not rotating, let's launch this again, see what you guys think. And I'm holding a bicycle wheel like this one. Remember all this stuff. And I'm holding it this way. I'm going to hold it this way so that it's rotating clockwise as viewed. Is that right? Yeah, clockwise as viewed from above. So I'm going to hold it like this. What is the direction of the rotational momentum of me and the the chair and this wheel, bicycle wheel. Anyway, it's all just the wheel. Is it up or down? No, wait. Wrong. I did it wrong. Counterclockwise. Sorry. It says counterclockwise, so let's do it that way. I think I said clockwise. I meant counterclockwise. You guys get it? Counterclockwise. It's tricky. I think I kind of messed that up a little bit, but hopefully you guys got it. Yeah, you can't redo the poll. I see. Sorry. Anyway, it's hopefully you got it. I'm sorry if you meant down. If it was clockwise, it would have been down. So if it's counterclockwise, it's up. So then, assume no external torque. If Harlow flips the wheel upside down, it's now rotating clockwise as viewed from above. Can you kind of picture that? So if I have the wheel and I'm rotating it, let's say we're looking down from above. If I started off counterclockwise and then I flip it around, look at that. Now it's going clockwise. So I'm actually literally flipping the rotational momentum direction. So the question for the demo is going to be what's going to happen to me if I'm sitting on the chair when I do that. So let's stop this chair. And let's point it over here. You can see my bike off in the distance there. I'm also going to put on the I'm going to change my audio so you don't mind. Okay, so we'll do the wheel second. We'll first do demonstration 1, and that will be, so this is just a regular chair, which I can then like spin around on it without falling, hopefully. And what I'm going to do is I'm going to take these two 5-kilogram masses, just to give a little extra boost here. I'm going to have my arms outstretched. I'm going to get myself going. I'm going to lift up my foot. So now there's no external torque. If I bring in the masses, what happens? Okay. Changes my omega, rotational speed, because there's no external torques, so I'm conserving angular momentum. Okay. So that one. Whoa. A little dizzy, sorry for that. Okay, so now this one. What I wanted to do was I'm going to hold one foot down so I'm not rotating this time, and I'm going to spin this so that it's counterclockwise as viewed from above. So this way, give it some spinning. I'll hold it like that, and I'm going to pick up my foot, and now flip it. Flip it. Flip it. Okay. So as this wheel is spinning, I'm going to actually stop myself by turning it up. So now, right now, the angular momentum of the whole system's up. If I turn it over, then I have to start spinning so that my angular momentum is up because I've changed the direction of this wheel to be down. So those are my 2 demos. Alrighty. Change my thingy. Okay. And go back to share. Harlow. Okay, we're going to do the recap, but also I want to make sure you guys are okay out there. Chat. There we go. Participants. There it is. I am a little dizzy. Okay. Let's go through both the demonstrations. Okay. Where's my participant list? There it is. So let's quickly just go through. So demonstration 1 was I began rotating at some particular value of omega with my arms outstretched. So that's large I, rotational inertia. And omega was fairly small. I didn't give myself much of a rotation. And L equals I times omega is some whatever value it is. I then bring the masses in, that decreases I. So there's no external torque. So rotational momentum must be the same. So I guess since I goes down, omega has to go up so that their product is the same. The demonstration 2, I was not rotating, but the bicycle wheel was going counterclockwise so that its rotational inertia was up. And then I flipped the wheel upside down, so its rotational inertia was now down. There's no external torques, so the rotational momentum of our whole system must be still up, and so therefore I started rotating counterclockwise. Makes sense? Aline, did you have a question?
Hi, yeah, I just had a question regarding the first poll, because there was something, wait, can you go back to the slide?
Yeah, sure. Oh, you mean the very, like these ones for the demonstration?
No, the very, very, very first one.
Oh, yeah. Yeah, this thing. Mm-hmm.
Yeah, I don't understand why it would be the Z one that changes, because I mean, regardless of how it turns, it like your thumb always points up, so that stays the same. So I don't understand why that one is the one that changes.
Yeah, that's true. So yeah, you're right. It doesn't change the direction, but it changes the amount, I guess, right? If the omega goes faster in this case, because you've the ball is given a sharp blow in the forward direction. It's still in the string, so it's still going around in a circle, but now omega gets bigger. So the question is, what's the change? What direction does the momentum change in? So if the angular momentum is up, as it is, and still up before and after, but it gets greater magnitude, then the change is up.
Okay, so it's just that basically if it was a vector, it would be a longer arrow?
Exactly, yeah.
Okay, all right, thank you so much.
You're welcome. And Veronica?
I just have a, hello, can you hear me?
Yes, I can, hi.
Oh, yeah, I just have a question about demonstration 2.
Yeah.
So you start by rotating the wheel counterclockwise, right? But what if you start at rest and rotating it clockwise? How would your motion change with that?
Yeah, well, when I got it rotating, I had my foot on the ground, so there was the external torque of the ground. But yeah, I guess we could try it where I was sitting on the chair and just start rotating the wheel. Whatever way I rotate the wheel, I'm going to start rotating the opposite way if there's 0 like total, I would think.
All right.
Makes sense?
Thank you.
Yeah, sure. And actually, Naomi, did you want to unmute?
Can you hear me?
Yes, I can, yeah.
Hi, so I was just wondering, why would the rotational momentum of the system still be up if there's no external torques? I'm just confused about that.
Well, the whole idea is that if there's no external torques, then the rotational momentum doesn't change. It's sort of at Kina's things, conservation of rotational inertia.
Okay, thank you.
Okay, so as soon as I lift my foot up off the ground, which I did before I flipped the wheel, then that's when you shouldn't have a change, I guess, in rotational inertia. All good questions. Okay, what is next? So we recapped them. This is, so real life example here is actually how do you ride a bike? Someone was asking me do I have to put some chains on my wheels in order to move, or is it possible without that? So yeah, I didn't put any chains on my wheels. What I did is I just really slowed down. I took back streets to get here. So normally I can ride in about 25 minutes to work. It took me about 35 minutes. So I just walked a couple times too if there was too much snow. So it was okay. But generally when you're riding a bike, there's some angular momentum of the wheels. And if gravity wants to tip you one way or the other, then those wheels will stabilize you, okay? Because they'll want to hold their angular momentum. This is why when you're teaching a kid to ride a bike, little kids, they want to go really, really slow because that's how you're used to getting to doing new things, right? If you're going to walk slow and then you get speed up. With a bike, it's actually easier if you go a little fast, a little bit. If you go a little faster, your wheels start spinning and then you're really riding. And that's because you've got more rotational momentum in your wheels if you're going a little faster. So spinning things can lead to stability. Oh geez. Okay, so why don't we do an actual problem? And this is about conservation of rotational momentum. So a 20 centimeter, so when you say 20 centimeters, I'm going to say that it is actually R1 equals 0.1 meters. 2 kilograms solid disc is rotating, and I can say M1 is equal to 2 kg at 200 RPM. Okay, so we can sort of sketch it here. Here's a disc, and let's say that omega I of 1 is 200 rotations per minute. A 20 centimeter, so another R2 is 0.1 meters. 1 kilogram loop, so I don't know how to draw a loop, but maybe like a donut kind of thing, is dropped straight down onto the disc. We'll call that 2. And this one, omega initial 2 is 0. It's not rotating at first. And then friction causes the loop to accelerate until it is riding on the disc. What is the final angular speed of the combined system? So omega final equals question mark. Okay. So what we're going to do is assume that it is a totally inelastic collision, I guess, in which angular momentum is conserved. It's going to lose some energy. But basically, there's no external torque. So if you were to, I guess if you want to draw your torque bar diagram or something like that, or angular momentum, you would say that L initial plus any external torques is equal, I guess, times time, right? So external impulse is going to equal L final. Anyway, point is that's 0. And so whatever initial rotational momentum is final. So this is rotational momentum does not change. That's the basic idea there. So the other thing that you need to know is that L is equal to I times omega. Let's put some more equations down here and simplify a diagram. You know that I1, since it's a disk, is going to be 1/2 times M1 times R1 squared. And you've got I2, since it's a loop, is just M2 times R2 squared. There's no half there. And so 1/2 M1 R1 squared plus 0 is equal to 1/2 M1. Oh, and that's, wait, forgot to do times the omega. It's I times omega. So that's times omega, 1 initial plus 0 equals 1/2 M R1 squared. Let's just times omega final plus M2 R2 squared omega final. Okay, let's also do the R1 equals R equals R2 equals R. We'll just call it R because they're both 10 centimeter radius. So what this is this is the L initial, because only one of them is spinning and the other one's 0. And then when they come together, they're both spinning with the same angular speed. So you just add those up. So I'm going to divide both sides by, let's do r squared over 2, so that I get just m1 omega initial 1 is equal to m1 times omega final plus 2 m2 omega final. So omega final, which we're trying to find here, is m1 over m1 plus 2 m2 times omega initial 1. So that's equal to 2 kilograms divided by 2 kilograms plus 2 times 1 times 200 RPM. So I got 100 RPM. So when you drop it, it slows down. So it's about half of initial. Okay, and maybe we don't need to convert to SI because it never asks you to. Just quickly go up here. Hamad, let's go unmute.
Hi, Professor. My question is about the demo that you did with the bicycle wheel, right?
Yeah.
So you're initially at rest, so your initial momentum is 0, but the wheel has a momentum, right?
Yes. Yes.
After you start spinning, right? You also have an initial momentum. So my question is, does the wheel lose momentum?
Well, it flips its momentum. It was up, and then if I just flip the wheel over, then suddenly it's way down, right? So it's changed its momentum because I flipped it upside down. So what I need to do is to compensate for that by having sort of twice as much rotational momentum, but in the upward direction.
Mm-hmm. So if you're solving a problem with that, you would consider yourself and the wheel as a system, right? Together?
Yeah, exactly. And there's no external torque on that system.
Right. That makes sense. Thank you.
Yeah, sure. Ethan, do you have a question?
Do you not have to consider friction part of the question?
Yeah, well, it is friction. So, but friction is an internal force. It's a really good question. I think friction is between the two discs. So actually, I should have done this. I should say here somewhere that red is system. So we're running out of here. System equals both loop and disk. So basically, a friction torque is internal.
Oh, okay. But if you were like to define the system as just one of the disks, then you would have to apply it.
Yeah, exactly. Then it would be external to that system.
Thank you.
Hey, you're welcome. Okay. All right, let me check my time here. Yeah, I think we should keep moving. Okay. So the next thing that we need to talk about is rotational kinetic energy. A rotating rigid body has kinetic energy because all the atoms in the object are in motion. So what we do when we have something that is rotating is we define a whole new thing called rotational kinetic energy, 1/2 I times omega squared. So if it's also moving, like if it's all, so this is around maybe its center of mass. If it's also got its center of mass moving, then you would add 1/2 mv squared, where v is the center of mass motion. So you sort of combine that particle approximation, for some people you assume it's not rotating, so 1/2 mv squared plus 1/2 I omega squared. So this fan for people in example. Just real life example of that is they have flywheels, which can actually store and provide energy. So this Porsche 911 hybrid test car actually uses a flywheel inside of it to store energy. So when you want to slow down, for example, normally the way brakes work is they press two brake pads against each other and dissipate the energy as through friction as internal thermal energy. And that's what slows down your car. But if you could take that energy and transfer it into an internal flywheel, you could brake and slow yourself down, but you still store that energy inside your car with the spinning flywheel. And so then if you can hook back into that, you could reuse that energy to speed up again and save energy rather than your brakes always just wasting this thermal energy. Let's do a quick poll question here for you. So this is sort of what I did. I brought in my arms and then I sped up. Omega got larger. So my question for you is, compared to this figure skater's initial rotational kinetic energy, how does the rotational kinetic energy change when she brings her arms in? Is it A, there's the same, B, it has increased, or C is smaller? It's a bit tricky. She's certainly going to be rotating faster. And let me actually write down why that is. Where's my pen? The reason is that I initial, omega initial equals I final, omega final. And what happens here is that, what should we write here? I initial is greater than I final. She decreases I. So omega final is greater than omega initial. Okay, let's see what people are saying here. This is one of the closest polls we've had in a while. 48% to 46%. It's either the same or it's larger. Okay, so the answer is it's larger. So this was a tricky one. And whoever 46% of you thought it was larger, it actually is. And the reason is because kinetic energy is actually equal to 1/2 I omega squared. So it's the squared that is the difference here. So another way of looking at it is it's 1/2 of I omega times omega. Okay, so remember that since L equals I omega is constant, then as omega increases, then the kinetic energy, which is 1/2 sort of L, I guess, times omega will increase. Okay, so let's say if I decreased my rotational inertia by a factor of 2, so half of what it originally was, then I'm going to be spinning faster by a factor of 2. Omega go up by a factor of 2, so those compensate. But my rotational kinetic energy, the I will go down by a factor of 2. The omega squared will go up by a factor of 4, and so I'll have double the kinetic energy. And so what happens is that the skater does work, or I actually do work, as she brings her arms in. She's actually doing positive work on herself because it takes a force over a distance. I don't know if Naomi, if you ever felt like you were doing work when you brought your hands in for these spins, but I kind of felt it, I guess, because they're being pulled out by the sort of centrifugal force. You're pulling against that and doing work. Okay, so she agrees. Good. I have an actual figure skater. That's good. Yeah, it's really weird. She's doing work on herself. So it is possible to be the system and to do work on yourself. So what happens is the internal kinetic energy, or sorry, internal chemical energy of the system goes down because she's burning calories, but then she pulls her arms in, and that does work on her body, which speeds her up. It's a really good point. Annie said that the system, there's no work. So it's sort of like, I guess what happens is the internal energy goes down and your kinetic energy goes up. So maybe it's not working. Anyway, this is the complete linear versus rotational analogy chart. So we did all these things before where we were saying SV and A is analogous to theta, omega, and alpha. The force is analogous to the torque, gives it this angular acceleration. So there's Newton's second law. The linear acceleration is the sort of the sum of all the forces. I don't know why I put those nets there. We usually put a little sum divided by the mass. The sum of all the torques divided by the rotational inertia gives you the angular acceleration. Now you have kinetic energy 1/2 mv squared, very analogous. Rotational kinetic energy is 1/2 I, which is analogous to mass, remember, times omega, which is analogous to speed squared. So it actually looks just the same. And then there's the momentum as well. P equals mv is analogous to L equals I times omega. So it's a nice little chart. Okay. 45. Yeah, I think I want to do another example of how this stuff works. And normally what happens is that rotational inertia is just something that's given in a question. You don't have to do, the only way to find, so this is a 0.5 kilogram basketball, which I happen to have. It's rolling along the ground at some 1 meters per second. What is the total kinetic energy? So if it's rolling, it's not just moving, it's also rotating because it's rolling without slipping. So this is not too bad. You're given rotational inertia of a hollow sphere because it's filled with air is 1/3 mr squared. So you've just got, here it is, it's rolling and it's going, right? And so we're going to assume rolling without slipping. And what that means, you have all these constraints. The important one here is that V, which is that speed, is equal to omega times r, where r is the radius of the thing. It doesn't give you the radius. But anyway, maybe it doesn't matter. I guess we'll see. So find k is the question mark. So what we're going to say is that k is equal to 1/2 mv squared plus 1/2 I omega squared. And then I is equal to 2/3 of m times r squared. And then also, so I can take that and plug it into here. And we can also take that omega is equal to v over r and plug that into here. So it's going to look like k is equal to, that's again 1/2 mv squared plus 1/2 of 2/3 mr squared times v over r squared. So let's do all this stuff. It's plus, there's 2/6, and there's an m, and then there's an r squared times v squared over r squared. So this is 1/2 mv squared. So a bunch of things are going to cancel. Let's get the red thing. Okay, r canceled, so that's good. Remember, I didn't know what the radius of the basketball was because it wasn't given. Doesn't matter, as it turns out. So I would just say that k is equal to 1/2 plus 2/6 mv squared. So that's kind of interesting. So k is equal to the lowest common denominator. You got 3/6 plus 2/6 of mv squared. You just get 5/6 mv squared. Okay, so that's equal to 5/6 times 0.5 times 1 meter per second squared. And I got kinetic energy equals 0.42 joules. Okay. Rohit, how are you?
Hi. I just had this might be a dumb question, but like similar to how the kinetic energies, like the translational and the rotational, like they add up.
Yeah.
Let's say if you had like a football or like a bullet that was spinning, and the angular momentum was in the same direction as the translational momentum, would they add up?
Yeah, they're still the exact same thing. The total energy of the bullet will be that rotational kinetic energy, like the total kinetic energy. It's got some energy of spinning, right? In that case, you're right. It's not rolling without slipping, but it has some spin to it, right? So, Thea, did you have a question?
Yes. I want to ask, like, in the past when we haven't learned the rotational energy, and we made this kind of questions like two balls, they collide together, and we calculate the kinetic energy, the translational kinetic energy, applying the conservation of energy. Does that mean in the past we are ignoring the rotational energy, or did they just cancel out each other?
No. We've just been ignoring it. Exactly. So in real pool, when you're actually playing with real billiard balls, they're actually rolling without slipping on the table, and that adds a whole extra layer of complexity. I'm not sure why, if we were able to, maybe if the rotation doesn't change much, maybe we're able to neglect it. But so far, that's what we've been doing, is either neglecting it or just assuming things were sliding on frictionless surfaces. Like if there's a puck sliding on a frictionless surface, then there is no rotation, right?
Okay, good. Thanks.
Okay, yeah, sure. Good to hear from both of you. Okay. Okay, so let's sum up. There's different kinds of energy. Kinetic energy due to the bulk motion of center of mass, 1/2 mv squared. Gravitational potential energy of the system plus the Earth is mg times y. There was spring potential energy of the system plus the spring, object plus the spring, 1/2 kx squared, where x is how much the spring is stretched or compressed away from its equilibrium. Now we have rotational kinetic energy, 1/2 I omega squared. We still have thermal energy, internal thermal energy or internal energy. So if the system includes two surfaces that are rubbing against one another, then you've got delta U internal is the magnitude or absolute value of the kinetic friction times the distance. So any system can possess any or all of these above types of energy. And you can transfer energy in or out of a system by doing work on it. That's sort of how I think of that. So another poll question for you. Let's think about this a little bit. This one, again, I think is going to be tricky for you. Let's see what you think. Poll. Pretty simple sounding question, isn't it? Trick here is you've got a solid disk released from rest, rolls without slipping down an incline, versus a box released from rest, which slides down a frictionless incline of the same angle, theta. Which reaches the bottom first? Okay, I'm going to stop you right there for a second. Let's do this twice. Let's end the polling, share the results, and then I'm going to actually ask the question right now. Is this ramp frictionless? Is my question. If not, which way does friction act on the disk as it rolls? it starts, it's not rotating at all because it starts at rest. It then starts rotating, I guess, clockwise, right? So if it's going to rotate clockwise, what's the torque around its axis, which is causing it to rotate clockwise? Where's that coming from? And what's the sort of the direction of that force? Let's do this relaunch polling. Same question as before. Which reaches the bottom first? I think I didn't like your answer. It's a hard one. Okay, so let's do 10 seconds. Click. I always like to hear from as many of you as possible. Okay. So a couple of ways of thinking of this. So certainly the box always wins. So one is that, yeah, if it's gonna have some clockwise torque, then the friction, static friction, must be to the left. So that's gonna slow down the whole thing. Another way of looking at it is thinking about conservation of energy and think of these bar charts. So now what you have is that initial of all these things equals the final. There's the system is the disk plus the Earth, okay? System equals disk plus Earth because you got the mgy. So some amount of height is going to change in both cases. You're going to reduce ug by the same amount. So then that has to go into energy. In the case of the disk, some of it will go into 1/2 mv squared, and some of it will go into 1/2 I omega squared. Whereas in the case of the box, it all goes in to just 1/2 mv squared, and so it goes faster. Twice as fast, or not twice as fast, but definitely faster. One way of looking at it in terms of actually working it out, you can just figure out the acceleration of a sliding object. So if you have that box going down, let's just do it by forces, right? It's pretty simple. You've just got, we'll define x. This is sort of review. You guys have done this a million times. Here's your normal force, surface on, we'll call it the object or something like that. Here's the force of gravity, the Earth on the object. Down, you go to the little thing. You say that the sum of the, I guess, AX is the sum of the forces in the X direction divided by the mass. It's mg sine theta divided by the mass. AX equals g sine theta. So you guys have done that a million times. Get the idea? Okay. As theta goes to, I guess, 0, then there's no acceleration, etc. Okay, this is the hard one. What is the acceleration of a solid disk rolling down a ramp? Okay. So solid disk has got I is equal to 1/2 mr squared. And so what you've got here is a thing is rotating and it's got AX. Again, we'll put X down the hill and Y up. Let's define plus is actually clockwise here, so that alpha is equal to A sub X over R. Call it equation 1. If we want to draw the force diagram, you've got the force of gravity of the Earth on the disk acting at the center. You've got the normal force right here, normal force of the surface on the disk acting up, and you've got the static friction acting up like that. Okay. And so the normal force is toward, so this is, by the way, axis of rotation is the center. okay, towards the axis. So 0 torque. There's no torque from the normal force. And then 0 gravitational torque, because it's also acting on the axis. So basically, all your torques is just coming from the static friction times R. This is R right here. And the sum of all the X forces now is mg sine theta minus F sub S. So what you've got here is A sub X, which is the sum of the X forces over M, is equal to mg sine theta minus the friction force divided by M. We can call that equation 2 if we want. And the alpha is equal to the sum of all the torques divided by the rotational inertia, is just Fs times R divided by 1/2 m times r squared. So actually alpha, to simplify it out, is 2Fs over m times r. We can call it equation 3. So we've got 3 equations and 3 unknowns, which are, you don't know A sub x, you don't know alpha, and you don't know F sub s. It's a self-adjusting force. So just solve for A sub x. So 2, we can rearrange that. M times A sub x is equal to mg sine theta minus F sub s, which means that F sub s, the friction, is equal to mg sine theta minus A, ma. So I'm going to plug this in, plug this and 1 into equation 3. So I've got A x over r is equal to 2 over mr times this thing for friction, mg sine theta minus max. And we can already eliminate some of these things. There's m's on tops and bottom of this. Okay, and there's an r here and r here. So we actually get, let me get a room here, but a x equals 2 times g sine theta minus 2ax. We can just solve that out for a sub x. So shift that over to the left. We've got 3ax is equal to 2g sine theta. So a sub x is equal to 2/3. Let's try it right. G sine theta. Sorry, once I try to go fast is when I slow down. Okay, so this is smaller. G sine theta. I wanted to show you that, and I overestimated time. It's 12:02. So if you have somewhere to be, this is you're free to go. Sorry for keeping you a little long. I would like you to start in on chapter 10 before Wednesday. You can see what's coming up. Midterm 5 is on chapter 9 and 10 on December 1st. Okay, let me stop recording. I'll see you on Wednesday.